Okay, this should be recording now. Okay, yeah, this is recording now. All right. I'll supplement the previous section if people really want to watch a recording. But coming back to the topic, we have drawn a voltage source and a current source based on the syntax on the left. So there are a couple of things that I would like to explain a little further. For example, why do we use V and why do we use I? And how do they turn into these diagrams? And this is where I'll start contributing to talking about the basic syntax of component. So we'll come back to this slide after we explain the next one. So you can build circuit components based on based on a bracketed list separated by comma. For example, if you like to compose the component of a short wire or an open circuit, what you can do is to put the three parameters here, which are wire option, wire shape, and current option. And those parameters don't really have names, so we're just using custom names for the parameters. So such a component defined by a bracketed list, once again, defines a wire of a specific option whose terminals, which means whose ending points, are determined by this parameter wire shape. And the current label or the arrow mark of the label that you will see, the arrow mark of the current and its label on the wire that you will see is defined by another optional parameter here called the current option. So the wire option here can be two words. It can be many more words, but for now we'll introduce two. One is called short, which means you just directly put a wire. The other one is called open, which means you put an open circuit. We'll talk about what's the difference between short circuit and open circuit on the right side. And you also have the parameter called wire shape, which follows the pattern of P-P. And this choice of P can be either an asterisk, which means you have a fully filled circle here, or it can be the letter O, which means you have this unfilled circle here. And last but not least, we have current option, which allows you to either or not put a current across the wire. If you do not want to put a current across the wire, you can just not talk about current option, and the computer will be like, okay, sure. So this will display some component that has the appearance defined by the above parameter. So let's look at the example usage, where we see that once again, we are drawing a path from 0, 0 to 2, 0, except now, rather than using the voltage source mark, which is V equals something something, we now have a short circuit. First of all, it's a short circuit because we know that the short label is at the first position of the bracketed list. Second of all, we have asterisk dash asterisk. So we can see that the top wire here has two endpoints that are filled. And last but not least, we use I equals I short to mark the arrow mark here. You can also change the position of the arrow mark, but that will require a little more Stack Overflow and a little more Google search that we're not going to talk about here. So similarly, you'll see how an open circuit is defined, where I draw an open circuit from 0, -2 to 2, -2, meaning that instead of having a wire here, I have no wire here. And as usual, the convention of open circuit is that we define its appearance by O-O, which means I'll have unfilled circles here being terminal of the open circuit. And last but not least, you see a slightly different way to address current option, which is F. So the I here stands for current and F here stands for flow. If you use the F option, then it will put the arrow mark above where the wire of the current or the wire of where the wire of the circuit is supposed to be. So in this case, you see that F does put the I open above. So let's come back to why we were able to define these voltage sources and current sources. So the voltage source here is defined by the label V, which means whenever you put V as your first argument, that means you're giving me a voltage source. Whenever you use I as your first component, it means that you're using I as the label of your component, which gives you a current source. Furthermore, you can also put things before the equal mark to define the sign or the orientation of a source. For example, by saying I greater than equal to I2, we see that we are able to draw a current I2 going through the current source. And this kind of syntax also differs from components to other components, which will take a little bit more exploration. But you can refer back to the documentation if you need anything. All right. Any question about wires and voltage sources? Okay. So before I move on to the next one, let me also show you how to use this document that we'll release later. So you see that this document will be released later, but this document is just the text version of what we have on here. So this document is once again the LaTeX version of what we have in the slideshow, which is once again a series of documentation and some example usages. So for example, you see the open circuit here and you see the short circuit here that has appeared before. There are a couple more sources, as we all know, which are dependent sources, and you'll also see a little more detail on the LaTeX document than the slideshow. Okay. And once again, these circuit diagrams should all be organized in subfiles so that it's easier to debug for you. Okay. Is it okay if I move on to resistor components now? Okay. Let's talk about other basic circuit components. So in 16AB, we mainly deal with these three basic circuit components, which are resistor, capacitor, inductor. If you have not heard of inductor, you'll be hearing about inductor very soon. I hope you don't regret about it. But the way that components are defined is, once again, we use a bracket list that is comma separated. Except this time, you see that the parameter is slightly different. Previously, we had wire option, wire shape, current option. This time we have component label. We still have a current option, but we have a new parameter called volt option, which allows you to put passive sign convention across the component. Keep in mind that the volt option does not secure a correct passive sign notation. You have to debug it, or have your senior mentors debug it. So once again, the parameters, component label is very similar. It's either R, C, or L, standing for their respective circuit components. Current option is as stated in the previous slide. You have either I equal or F equal, and you can also decide the orientation of your labels based on what we're going to talk about here later. And last but not least, you have volt option, which is what grants you the voltage sign convention. And let's look at the example usage here. So first we have a resistor being plotted from 0, 0 to 2, 0. So let's try to dissect this statement here. We first have R equals R1. So I can either say R, which would just give me a resistor without any label, or I can add equals some kind of expression to give this resistor a label that shows on the graph. For example, I have R1 being the label of the resistor. Then I say F from the left to the right equals IR1, which gives me an arrow from the left to the right that says IR1. Now notice that if I flip the sign of this greater or equal to less than or equal to, I will get a wrong passive sign convention, which is another thing to think about if you're going to test people on passive sign convention. So that's one way of using LaTeX. Last but not least, I have V underscore equal, and then another expression that you see here. The reason why I put V underscore equal is because if I put something else like V equals, then what happens is that the voltage will be automatically set to above. Actually, rather than saying that, let me give you a demonstration of what happens. So I'm going back to the LaTeX, and I'm going to directly edit one of the figures I have here. I'm going to change this underscore equal from the V to just an equal sign, and let's see what happens. Oh, okay, it turns out being fine. All right, but what if I do up equal? So if I do up equal, then you will see here that VR1 directly conflicts the position of R1, which is why sometimes you want to know the position of your label. So once again, you can identify the position of your labeling using something before the equal. There are the four choices. If you're going upwards, use the upwards mark, which is the exponent. If you're going down, use the underscore. If you're going left, use the right to left, which is less than. If you're going right to the component, you can use the from left to right, which is a greater than symbol. Okay, now let's change this back. And notice that even if I'm, oh wait, is that a?
There's a question.
Yeah. Oh yeah.
If you want to write, like if the circuit element is going like, let's say it's on like the right side, how do you need to pass the right sideways or the side?
Then that will be when we use left. Then that would be when we use the left and the right. So if you have a vertical, actually let's do an experiment here. So let's say that I'm going to have this go from 2, 2 to 2, 0. And I set it to be left equal. Then after compiling, you see that so first of all, we're drawing a path across different set of coordinates, right? So now the resistor is vertical. And second of all, we note the voltage to be at the left side because we said V less than equal. So now the voltage is at the left side. So whether you can actually use the left side or the right side also depends on where how your resistor is oriented. I can also orient my resistor in a diagonal position, which would do something like this. And as we wait for it to compile, we'll then see that it is indeed oriented on the diagonal position. My voltage is still on the left side, and this will still work out.
Nice.
I'll keep this in the documentation because it might be helpful. Okay. So that was resistor. Capacitors are defined in a very similar manner, and so are inductors here. Keep in mind that for anything related to voltage in LaTeX, the general default is that the positive side of your voltage will be located on your starting coordinate, and the negative side of your voltage will be located on your ending coordinate. So for example, I'm going from 0, 0 to 2, 0. So the default orientation was going from left to right, right? And then here I adjusted the settings a little bit so that it goes a little bit different. And in general, if you want to keep a correct passive sign convention, then a very simple trick is to put all of your symbols before the equal sign to be same as each other. For example, I'm noting the current sign, which is being put as F here, and the voltage sign with the same less than or equal to and less than or equal. And this sets my passive sign notation for capacitor to be corrected. Okay.
So is it the arrow on the like the B argument that changes the passive sign like plus minus? But which one actually plays out?
The plus minus is changed by the V argument here. And by default, it goes from your starting to end. So you notice that the capacitors doesn't go from start to end because I edited it using the V argument. So I can also say F is equal to and V is equal to, and it should be set at the same direction. So similarly, current by default flows from the starting to the end, which is why sometimes when you write voltage sources, you might notice that your voltage sources are kind of like flipped, right? So there are a couple of ways to go against that. One is that you just switch your starting and ending coordinate and it will work out. The second one is you can add some kind of additional parameter, which I'll talk about later. Okay, and last but not least, we have an inductor, which works very similarly. Any other things that I should clarify about this? Okay. So then, since we have talked about putting circuit components on circuit, let's also think about putting non-circuit components on circuit. So for example, there are a couple of non-circuit components when put on circuit can give great effects. Say I'm working on a design question today, and I want an unknown component that is not supposed to take the form of a capacitor or a resistor. Rather, I want this unknown component to be a rectangle. So I put the rectangle on the wire, right? And then I have people guess about what this rectangle is. Something like that might motivate us to put a non-circuit component onto a wire. So I'm going to talk about the basics way of doing this first. First of all, we mainly use this mechanism called node in Circuitikz. And node happens to be a general mechanism across the Tix library as well, which we'll see later, and you'll probably see in CS17 later as well. So there are two ways of writing a node. The first way is we have a node appear in a path. In this case, the syntax of the node follows as node, and then we have another bracket standing for options. There are a lot of options for node that we'll not go through, but you'll be able to reference the documentation. And then there's parentheses, which is name, and we have a curly bracket, which stands for content. So let's talk about the parameters. But before that, let me note that the node here that we're referring to actually just stands for a Tix object. It is just an object that you can somehow customize to your own liking. So no need to think of the node as some kind of complex symbol like a binary tree search node or a node in a doubly linked list. Just think of the node as a LaTeX object. Okay, so parameters. Once, as previously mentioned, the options of node is very variant. So you can reference the documentation and decide what kind of options you want, or sometimes if you need Stack Overflow. And you can once again reference the cookbooks for your demands. Now the name of the node. So we name a node so that we can refer to it later. So you can think of the name or this piece of text that you put in the parentheses for a node as a variable name, where in LaTeX, to reference this node in some kind of path later, you have to use the name of the node to refer to it. So it really works like a Python variable name. Last but not least, we have a curly bracket surrounding content, which just stands for the content text of a node. If you do not wish to put any text in your node, please put an empty curly bracket or else LaTeX will scream at you. Okay, and last but not least, this command will display a node according to the shape you put in. So let's look at the basic examples of nodes in a path. So one notable example of doing that is the ground node in a circuit. For example, we can say node, and then the option here I'm going to put ground, which gives me a ground node. And as mentioned before, I must put a curly bracket here. Maybe the node can be unnamed, but the node has to be at least have an empty content. So by putting the ground node after, I can generate a ground node at around the 0, 0 position. But there's also something important to note is that if you want a node to be at some coordinate x, you have to put the node before the coordinate x. The reason why this works is because this is the first coordinate I'm working with, so it doesn't really matter. But actually, let's try to change that a little bit. Let me try to hide this once again. I'm going to go to a different place in LaTeX where I'm going to try edit that exact circuit and let's see what happens. So the circuit I'm dealing with is this one, where you see there's a chip thing. I'm going to put the node in front of the 0, 0, and let's see what happens. So nothing really changes because it's our first coordinate here. But let's try putting node ground in a different coordinate. For example, instead of putting it in front of after the 7, 0, I'm going to put it after the 4, 0, and let's see what kind of bug this causes. So as you see now, the ground node is actually put at 4, 0 because the code on the left-hand side I have here has the node ground immediately after the coordinate 4, 0, which causes the node ground to be there. And this is not the result we wanted. So once again, to put a node at a specific coordinate, we must put it after that exact coordinate. So let's recompile and see what happens. Okay, so you see now the ground node is back to where it should be. Once again, this rule only applies if you're not working with the first coordinate. If you're working with the first coordinate, then generally this is not too big of a deal. Okay. So that is node in a path. There are also other options of there are also other purposes of putting nodes within a path, but for now we'll mention ground node as one of the applications. Additionally, you'll also see more other things being able to put as a node, but we'll talk about that later as well. For now, any question about ground nodes? Okay. Then let's talk about the second type of node, which is an independent item from, as you see, the /draw command here. So this kind of command draws a node very similarly to before, but it draws a node outside the /draw defined path, which means now it also needs to have a now it also has to have a coordinate, because we used to define the coordinate of a node by what coordinate precedes it, right? But this time we have to have a coordinate for the node itself. And as usual, we also have option, we also have name, we also have content. Name is once again optional. So the parameters stay really similar. And now I'm just going to go through the example usage of what this is doing. So I see that here I have /node, which defines a separate node. And we have these different options here. So as you can see, you can adjust the options of a node to fully customize this LaTeX object. In this case, I'm using a rectangle. I'm using the mode draw. I'm filling that rectangle with a white color. I'm using a minimum width and a minimum height. And I'm putting this node at 5.5, 0. The reason why I know that is because I can reference the syntax on the left-hand side where it says add cohort. Last but not least, I put a sign in there to show the label I want to put in. Chip r, chip, r equals 0 ohm, chip, r equals 0 ohm. So there are also a couple of ways in which we can draw this diagram. For example, we can experiment around using an inline node instead of using an outline node. And we can try to hide the floating meeting controls again and edit the circuit here to see what we can do. What I'm going to do in this case is I'm going to copy paste the node I used for a rectangle here. And I'm going to see what happens if I put the node here instead. And let's make this a case study of how nodes work. I'm going to draw a node here. Maybe add an option here. And let's see what this does to the circuit. Oh, and I also forgot to delete this one. But sometimes you'll see that it's easier to, well, actually, I'll wait for the circuit to compile before I continue. Okay, so sometimes you'll see that it's easier to edit one type of node instead of the other. So for example, in this case, the code on the left-hand side doesn't really compile well because we then have to do some more different ways of fine-tuning. So at this kind of stage, we can kind of fiddle with the optional parameters and see what happens. And this time we see that it moves slightly to the left, slightly to the middle, but then we also have to do extra fiddling to do with this. So sometimes it is actually easier to use specific types of nodes instead of other types. And in this case, we chose to settle with the independent node in the end because we know it's easier to fiddle with. The only people who are going to look at your LaTeX code is your colleague and yourself. So really just focus on how to write the LaTeX code in the best way that you and your colleague can understand. Okay, so that's a small lesson on like how to choose different nodes to work with. In general, you can experiment with both kinds of nodes and see which one works a little better than others. Right. So that's basically that's a short lesson on nodes. Any questions so far? Are we all okay with nodes? Do you want to give like a thumbs up or down about how do you feel about nodes? Okay, we're absorbing really quickly. Okay, here's another example usage of node that might hurt your head, which is the Markov chain. But 16A also has to use this as a state transition system. So as you can see, in this case, we're not using an in-path node, but we're using an outside node to perfectly draw out these state transition diagrams. You might also see that there are some in-path nodes here, for example, this node, and then curly bracket 0.8, which is used as an in-path node on one of the edge of the graph. And this is convenient. This is at least more convenient than writing out another node, because the node that we put in path is usually dependent on the previous wire or the previous path it's using. In this case, we see that the 0.8 should be dependent on the path we use to loop on C, which is why we use the in-path node. So in general, if you want to judge whether you want to use an in-path or an out-of-path node, it depends on whether your node is defined by or depends on a path location. Okay, should we move on? Are we ready for op-amps? Unfortunate. Okay, but before we talk, oh yeah.
So so when you're going from D to E and then E to D, you have bend right code both. Why is that?
Oh yeah. So actually, yeah, it will give a good experiment. So let's go back to the code that references this graph, which is here. So I'm going to show what happens if you don't do the bend right and bend left. So let me directly delete these. And we let it compile for a bit. Okay, so what happens in this case is that if we don't bend the edge, then they're all on the same path, right? Because the shortest path from D to E is the shortest path from E to D. So they're also all stacked together. And what happens in the end is that we have this double arrow, which kind of works, but it's not as aesthetic as the previous one, right?
Or I guess my question is, what is it bending relative to?
The bending is relative to the center of the edge. So if I say bend right, then usually what that means is it bends it according to a specific direction along the polar coordinates.
Oh, it depends on the direction. I think maybe you take the arrow and put it upright, and it's left or right based on that. Does that track?
Yeah, basically. Yeah. So for example, all of the things I have here are bent right, so that they are all on this kind of same orientation along its along how it's bent. So if I do bend left, then the signs then you can see that, for example, this might be retracted to the inside, and these two arrows will flip places with each other. In general, you can think of bending right as going outwards. For example, this one bent right is going outwards, and bend left is kind of going inwards. Okay. And you can also, funnily, you can also adjust how much you want to bend right, but that's another optional parameter in LaTeX. So as you can see, TIX has a lot of different optional parameters to work with. All right, other questions? Okay. If not, then we'll talk about op-amps. So in op-amps, we, first of all, before talking about op-amp, let me show you a very cool trick to write path once again. So previously we learned how to write path between two coordinates, right? But you can also write paths based on one coordinate in another increment. So our previous approach of graphing circuit was that we try to graph some kind of plotting paper, right? And then we try to define, for example, maybe my ground node should be at 0,0. Maybe my other node should be at 3,0. And I very precisely calculate where are the coordinates of each. And at the end, I'll have to add up a bunch of coordinates together to get the position of some kind of resistor, right? For example, if I graph like a low pass filter here, then what happens is that I'll have to calculate the position of a capacitor based on this resistor here and that wire here and that ground node here. But one trick that saves us from that that tedious computation, which none of us actually thought about before, was using relative positioning, which is available in TICS using the plus mark. So let's look at the documentation. Backslash draw core to, once again, we have this component as defined before, but instead of having a core 2, we have plus increment, which means we're able to add an increment to the previous coordinate and make it the second coordinate of the path. So let's look at let's directly look at the right example usage. In this case, we are drawing from, first of all, we're drawing a voltage source from 0, 0. But this time, we're not using the coordinate 2, 0. We're adding 2, 0 to its original coordinate, which is why I then get 2 units right as the end of the voltage source. As you can see, the positive sign is indeed aligned to the starting coordinate, and the negative sign is indeed aligned to the ending coordinate, which is as we talked about how voltage sources work. Now you can see a very similar trend here, where we're drawing from the origin, but according to the increment, we're going left 2 units and down 1 unit, which is why we have this diagonal voltage source. And once again, the positive sign aligns to the starting coordinate, and the negative sign aligns to the ending coordinate. Once again, I have these different little labels here to help me figure things out. Okay, any questions about how to use relative positioning? Okay, so the reason why relative positioning is useful is because we have to deal with op-amps, which, as you see, is this little cute node here, I guess, but it's very difficult to find the exact points along which V out, V plus and V minus is located at. At this kind of stage, to get the coordinate of these points, we can define nodes at these coordinates. And very gladly, we have the syntax to do just that. So let me introduce you to the syntax here called node op-amp name content. So it works exactly like a ground node, except now it can have a name and it can also have a content. So in this case, we see that this is an inline node with op-amp being an option. So another interesting point is that you can have some kind of keyword have space inside and still be a keyword in LaTeX, unlike in other programming languages. So let's talk about how op-amp works by trying to analyze this example. So the begin center here and the end center here just serves to center the circuit picture we have here. Begin Circuitikz and end Circuitikz serves to start a Circuitikz environment. Now we have backslash draw here. We're drawing a node at 0, 0 because we see that the node is put right after the coordinate 0, 0. So we have an op-amp at here. And then what I'm going to do is I'm going to first define another node at negative 2.5, 0.5, which I'll define a node left to the current point. So this left here is an option. So this node is going to be located right left to the point negative 2.5, 0.5, which is around here. So the node is here, left to it. And the node's label is going to be B plus. So I have successfully put a B plus here. And then I do the same thing for B minus, which would be left to the point of negative 2.5, negative 0.5. And the B minus is right left to the point I defined here. Now, I am actually going to also have these different nodes connect to the positive and the negative end of the op-amp. So you can reference a node as op-amp, right? And then we name this node op-amp here so that we can reference its positive and its negative terminal here. So if I say too short op-amp dot plus, then I'm drawing a path, first of all, from this node here to the positive node of the op-amp. But what I feel in this path is this short bracket list where I give an entire wire, right? And furthermore, I give this shape O dash, which means I'll have a unfilled circle and I'll have no circle at the end of the wire. Now I do a very similar thing with op-amp minus, so I have a terminal free converter. Another very convenient thing is that if you want to connect some other thing to these terminals, you know that these terminals have the points negative 2.5 and 0.5 because you have to find the nodes to be here instead of wherever op-amp plus or op-amp minus is. So that's another convenient point. Last but not least, I will have the output point of op-amp, which is here, that we don't know the exact coordinate for, but we can use a variable name to reference to. And I'm going to put a node right to where the location is, I'm going to put the node text as vi. And here's how we generate an overall labeled append picture. Any questions? Does this look friendly at all? You don't have to understand this immediately, but I'm sure, but this is a general demonstration of how we can reference different places of the append by saying append dot plus, append dot minus, and append dot out. And you can think of this as very similar to how we usually get attributes of an object. LaTeX is also somehow developed as a programming language, albeit as a markup language. So it does preserve these kind of properties that are kind of computer sciencey and programming. Okay. So with that being said, let's talk about another append, which is a comparator. So from now on, we're going to be presenting you different cookbooks that you can just copy paste into the assignment. So first of all, we see that the left-hand side code, or at least the top portion of the left-hand side code, is completely similar to what we had before, which is just the operator, which is just the append itself. But another thing about comparator is that it has to have this like small symbol in the middle of the triangle, right? So here's where we start to use here's where we start to use some kind of absolute positioning or some kind of other way to draw out this short symbol here. So first of all, we know that the append is drawn at the coordinate 0, 0. So the center here of the append, which is the center of this triangle, should be at 0, 0. So if I want to draw my symbol at the center of this triangle, what I need to do is to write, what I can do here is to write a small symbol here using some kind of like dark lines, right? And it should also be centered at 0, 0. When we think about dark lines, maybe the first thing we think about is a wire. So we could use a wire, and I'll just put a very small piece of wire here that is not related to the circuit at all, but still shows you that this is a comparator by putting out this symbol here using a wire. So a wire can also be used for annotation purposes, for example, in this one. But it's rarely used like that. This is just one of the applications. Okay. Otherwise, what we have is we then try to draw the VDE and VSS using a short option there with the shape -O, which means I start without any terminal and I end with a circle. Right. Any question about what all of these is? Yeah.
Is there any better way to literally draw certain component?
I tried searching, but there was none. Another way is just to say in the question that this is a comparator, but I guess that might be a little confusing in terms of a content perspective. And I say that because I tried that. Okay. Other questions? Okay. So last but not least, here's another cookbook for append, which is an inverting amplifier, which 68 people might want to look at. So this time I'm going to re-dissect the circuit for you and let's see what happens. So first of all, I still have this begin Circuitikz and end Circuitikz. I have this scale because I wanted to scale the inverting amplifier to be smaller. So in this case, you can control how big your circuit diagram becomes. This is not totally reflective of what 0.7 should look like, but you'll see how 0.7 is on your worksheet. And now I'm going to start a \draw command. I'm first going to once again define the append node at 0, 0, which is going to be named AMP. So we're switching up the names a little here. And now I'm going to start a node at the negative node of append, which is around here. So I'm going to draw a white. So first, let's look at let's pretend we're a scheme interpreter and look at the code section by section. So I'm going to first read this section, the negative node to short plus 0, 1. So I know that I'm going to draw a path from where I am now, 1 unit above. And what I should feel in the path is the short, which is the wire, which is why we see a vertical upwards here. And then I define a coordinate here by saying coordinate, and I say top left. And this will help me later as I define another coordinate for me to reference later. So I'm going to call this point top left, using this a little bit new syntax. You can also think of this as just defining a node here. So now I'm currently at top left, and I'm going to read the next segment, which is 2, and then a resistor, and then here's something that I need to think about. So this, let's first talk about the shorthand position. So this shorthand position means go horizontal and then go vertical. So it will locate you to a corner where it will locate you to the corner of the path where you go horizontal and then vertical. Horizontal, vertical, corners here. So I'm going to draw something until here. This is where I'll end up with. Well, you can indeed just define another coordinate that says top right here, but in this case, the shorthand notation is also useful. So now that I know I'm going to go from the top left corner to the top right corner, I just need to think about what I'm going to fill in. And what I fill in ends up being the resistor Rf. So as I have filled up this horizontal section, I'm now going to go down. And where am I going to go down towards? Well, I'm going down to the output node of the amplifier, which means I should fill this section with a short wire, which is why we have short here. Okay, so now we have finished going down vertically. We'll do this interactively during the cookbook section. For now, I'm just trying to dissect the circuit first. Okay, so afterwards, I'm currently at the output node. And what can someone tell me what this 2 short plus 1, 0 should do? Yeah.
That should send I don't know the plus,
Mhm.
but the 2 short, we should send it to a short, like no wire, we can open circuit from the
Yeah. And then, yeah, that was exactly. And then what is the plus 1, 0?
Relative?
Yeah, it's a relative. So 1, 0 sends me to how many units? Where?
Relative to where it started.
Yeah.
Where that top end component started.
Yeah, exactly right. And then the 1, 0 part means I'm going right for 1 unit. So that's where the 1 comes in, because 1 is at the x position and 0 is the y position, which means I don't go up and I don't go down. So I go right 1 unit. So now I'm stuck here, and that's where I'll sit. I'm stopping at an open circle. And last but not least, I can draw an open circuit to try to end this kind of circuit. I can draw an open circuit to end this section, right? So then I fill in an open circuit with the label being text out. And I'm going to send the open circuit's end to, well, here's the plus, right? And then I have 0, -2. 0, -2. So how many units am I going left or right? Yeah, 0. Right. And then how many units am I going down? 2. Okay, yeah, 2 units. Do JCs get this? Okay, thank you. All right, so now I have finished one part of the op-amp. I have not finished this part. I have also not finished this part. And there are still a lot of things to go, right? But our current position is at like this random ground node that I cannot go from there to there. So what I do is I stop a path here. And I start another path by noting another coordinate without saying 2. So that starts the second path.
If you have a bunch of things use like this,
Yeah.
You use like the plus, is it implied that it's relative to the previous two?
Yeah, anything plus coordinate means relative.
Okay, so it's stack on each other.
Yeah, you can stack on each other. Which is why our code is also organized like this, so that you can stack things on each other and still be able to read this. Because if we learn anything from project scheme, is please format your code correctly.
Oh, so
All right, so let's go on to the negative node, and we're going to build out this resistor part, which once again, relative position, -2, 0, so going left 0 units, going left 2 units. And then now, here I'm going to have a little bit of special voltage source, which I can produce by adding another alphabet in front of V. So this might give you if you add a C in front of V, for example, it gives you a dependent voltage source. In this case, SV gives you this voltage source with an S in between, which might stand for AC or something. So then I'm sending this voltage source end to where it is 2 units lower than where we are now. And last but not least, I do the same thing for VREF. Okay, any question we have about how to dissect a latex diagram? Okay, let me check how much time we have left. Okay, that's okay. All right, so since we have been presenting cookbooks, and now we'll be presenting more cookbooks. And all of these cookbooks are made by our other content mentor, just to attribute. Okay, I did not code any of this, which these codes are beautifully written. So I encourage you to explore how these codes are differently styled. Okay, and I'm also going to do this interactively. Okay, so I'm going to try to build a voltage divider from scratch here, which I'll show you how to. So first of all, I'm going to go back to my LaTeX project, and as talked about before, whenever we generate a circuit diagram, what we want to do is to build a new file for each circuit so that it's easier to manage, right? And the reason why I was able to compile, I was able to press Control S, press compile on the circuit diagram is because there's this secret setting in the menu of the Overleaf project, which guides you to a main document at which Overleaf can work at. So if you go to another file that is not compilable and you press Control S here, it will not compile the uncompilable. It will compile the main document. This is pretty useful. So it might be the takeaway of this section if you forget anything about circuits. But let's try to draw a diagram here, which would be, what's that called again? Voltage divider. Oops, and let me rename this a little. Okay, and what I'm going to do here is I'm going to first type the subsection title, and what I'm going to do later is I'm going to use the \input command. So what this command does is it directly copy pastes a section of LaTeX document into your current document. So essentially, you can insert other documents into here without using tens or like thousands of lines. You can copy paste with one line. And I believe that is a good thing for computer science students. So let me quickly navigate to this figure, and I'm going to start editing this figure.
Did I increase the size of the evidence? Or like zooming?
As in like,
yeah.
okay, yeah, sure, you can do this. Okay, so let's start with a voltage divider. So as previously stated, we want to put this in the center. I'm going to say begin center and end center. So this center is my entire circuit graph, right? And then I'm going to have to type begin Circuitikz and end Circuitikz. And don't forget the American here, which I spelled wrong. Okay, so let's remind ourselves of how a voltage divider looks like. So I'm going to have to draw a loop, but I can start from the voltage source here, and then once I have the voltage source, I go up and then go right. So that's like that's like a voltage source from here to here, and then another right short wire from here to here. And then later, I'm going to have to draw two resistors all downwards with a passive sign combination on the right side, and I'm going to go left, and I'm going to go left. So let's go through these. Let's go through all of these requirements one by one. So first of all, I have to draw, and let's say that I start at the lower bottom corner, which is 0, 0. So what I'm going to do from 0, 0 is then I'm going to first draw a voltage source upwards, right? So assuming that the comfortable distance between resistor the comfortable distance for one resistor is around 2 units. So let's say that this is 4 units. So I'm going to draw a voltage source. And usually the way I format my code is like this. So I say a coordinate and then I say 2 from there on, 2 from the second half. So 2, and then I'm going to have a voltage source here. And then that was voltage source. So I'm going to put V equals Vs here. And since the positive sign should start at the starting coordinate, I'm going to press a comma invert so that I can invert my voltage sign. Okay, and then relative positioning. Okay, let's see what this does.
You can try to guess rid of it.
Exactly. Okay, so let's put a semicolon. This is the mandatory thing in backslash rule. So let's remember that next time. Okay, so we do see a voltage source that's sliding upwards, and we're going from 0, 0 to 0, 4. As you can see, it tries to center the image. Okay, so from there on, I want to go rightwards, right? And I'm going to go rightwards with a short circuit, but anyone wants to suggest how many units we go right? Okay, how do I do that? Okay, let's write it out. This is becoming like a 618 lecture. Okay, this works. And now I'm going to code two more resistors downwards. So I'm going to type out the basics here, which is that I'm going to go down 2 units each. Oops, I have to do it capitally. I tried that, but the minus is actually used for drawing edges. So minus is already taken, which is why we're using plus and then using negative increments. Okay, and last but not least, we can either draw another thing here, or we can just end with a ground node. Either way works. In the case we end with a ground node, we want to do this instead. Okay, so I'm going to draw the ground node here to save up some space. All right, so I'm drawing this out, and this should give me the resistors that are supposed to be there. Okay, so we do see a resistor, we do see a ground node here. Everything looks perfect, but we're missing the labels. Right. So let me go back to the label, the picture here, and I cannot zoom out in Google's. Yikes. Okay, Google size needs another reform. But can someone, without looking at the code at the left, tell me how do I like do these labels? Okay, yeah. So L equals works for doing the label, right? So let's do L equals R1 and L equals R2. Okay, so to orient this label to the left side, we can then use the L less than or equal to, right? Okay. So underscore would work in some context. We can see how it works out here. Oh, yeah. So in this case, L only accepts underscore. So we have to use underscore. The L here stands for inside or outside the circuit. Underscore usually means inside the circuit. Okay. But if we use IMV, we'll be able to use other things. Okay. So in this case, my label is VR1 and it's to the right side, right? And I also have these passive sign notation. So what do I do here? So we can try that.
I mean, I would suspect, wait, so if we find that the label uses an underscore and over to be on inside or outside, but the label uses left and right.
Yeah, but the voltage can use left and right. So there's kind of like this cheating move here.
So label, so label outside.
Yeah, voltage has a different syntax.
Yeah,
yeah, that's pretty weird. Okay. So in this case, using the upside uses the alt context, which is that you can just put it outwards. So using up is an option.
Yeah.
The other option is that we can use left equal or up right equal. And once again, the left equal and right equal depends on the sign of the resistor. So sometimes it's not so intuitive to use. Yeah. Yeah. Yeah, that'll be a way easier solution. But in this case, we kind of collide with each other. But what we can do instead is we can try this. Oh wait, never mind. You do have to. Okay, so it's like different syntax here and different parameters here. So sometimes this works and the other thing doesn't. Okay, in this case, using the underscore might be a little stabler. So we can try everything out and see what happens. In this case, underscore doesn't work. So R just has to go with the equal. And we can use an L here. Alternatively, you can also write another note here to make sure that it's on the left. So there are a lot of ways to write things out. Yeah, some are better than this. Oh my god. Okay. Yeah, good question. So yeah, it's from the way you draw it. So for example, in this case is you can think of it as the default is being left on the circuit for some reason. Yeah, whenever you can, just to get the maximum control out of this. Okay, so once again, you can imagine upwards as out of and underscore as in of. Okay, so that's a voltage divider. And miraculously, we arrive at the same thing here. I don't know why, but anyways, here's how a voltage divider may be built. Okay, and then extra credit for 16A. So we have a special package in 16A that other classes don't have. So we can do a special thing here, which is to get the custom environment working. So there's a special package in which by which you can define different terms and put different figures together. In this case, our package looks like this. And other courses might have this package as well, I just don't know. Okay, so our course has this kind of package that allows us to put things in definition boxes. So if you're interested in using it, you can also research it. Okay, let's pick something else to write a thing for. For example, maybe a low pass filter is a good choice. I'm trying to save time here. Okay, so I'll upload the other cookbooks onto this project later, but for now, let's also try another cookbook here, which is the low pass filter. Actually, let's try the band pass filter instead, because that will probably give us the most knowledge we need. Alternatively, yes, you can probably use ChatGPT. I just don't know how good ChatGPT is yet. Okay, so let's try to insert this place here. And so here's a convenient thing, which is that if you use the inputs with an absolute with an absolute measure for like getting your address, then Overleaf will be able to directly navigate you to different documents you have in the repository. But the cost of using absolute address is that when you switch over to the repository for the next semester, all of your address are going to be invalidated because your repo name changes, which means your parent directory name changes, and every address is going to not work. So if you can continue using relative address. Okay, so in this case, I'm going to start working on this LaTeX. Once again, I'm going to begin center, end center, begin Circuitikz. Sometimes it auto-completes, sometimes it doesn't. The Overleaf just does not like to be consistent. Okay, and American. So let's first try to figure out what a bandpass filter has. Okay, so first we need to draw out this small section, and then we have to figure out the op-amp, and then we have to figure out the right side. But usually the trick is that start with the op-amp first, because you want to center op-amp at some kind of position. And everything else's position depends on your op-amp. So op-amp is like your lowest level object class, and you have to build upwards, which means op-amp is our op-amp will become our priority. Okay, so that's a small design choice to make. So I'm going to first define a node at 0, 0 once again, because it's easier to deal with. And I'm going to call this node M, just to keep the convention going. Once again, it has to have a curly bracket. Okay, and I'm going to start something from maybe the negative side of the node. So what the negative side of the node does is it does this thing that we've seen in an inverting amplifier, right? It does this rectangular shape and then goes back to the out. Bless you. So what I'll do in this case is, so I'm starting from the negative node. I'm starting from a negative node, right? What should my wire do after I reach the negative node? Yeah. Oh wait, yeah, we're right. Okay, let's put this in, and then the semicolon here. Right. So what do we do with what should we do for the wire here? It has to go upwards, right? So since this has to go upwards, what I need to do is I need to say, first of all, I need a 2, and then I need a component here, which should be a short circuit. And then what I do after the short circuit is I want to know where does the short circuit end. In this case, it ends around 1 unit above it. So what I can say is plus 0, 1. And let's see how this plays out. Okay, So we do see an op-amp with some kind of short circuit going 1 unit above its negative node. What I need to do then is to complete this kind of turn, right? And we're going to use the syntax that we used before because we don't know exactly where amp out is. But we want our ending place to be at the same vertical axis with the output node. So what I'm going to do is to directly use the context we've used here. And then I'm going to samely use the two syntax. And I know that I'm going to fill out a short circuit here, but the position at which I'm going to fill to is the right upper corner or the horizontal vertical corner between this coordinate and here. That means I also should define this coordinate first. Okay, so I'm going to define here. And I'm going to stop at, once again, the output node. And then I'm going to, since I'm still at the corner now, I then have to fill out a wire so that I can go out to the output node. Okay, so once again, this line is for climbing out of the negative node. The second line, which has the corner there, is for me to build a wire such that I can go back to this horizontal vertical corner. And last but not least, I do too short to go to the output node. And what I can do later is, once I have finished this buffer, what I can do later is just to finish the rest of the circuit. So we're kind of running out of time since it's 4:45, but any lasting questions?
Oh,
yeah.
Wait, I saw it in this like wall.
Mm.
Using like the rod on the and stuff.
Mm.
You usually the SI unit, the X factor for units.
Oh wait, so the omega thing.
I think when you do like X amount of
Oh yeah, so I just use / omega because I don't. I haven't been using the SI unit thing yet, and omega happens to just be like the probable thing I can do. Okay.
You should do
Okay, yeah, I'll try that. What's the difference then?
It makes spacing like easier.
Oh, I see. Yeah.
And also like it's easier to like make random version units there.
Okay, yeah, I'll think about that.
Like no
Right.
yeah.
Yeah. Right. Other questions going on? Yeah.
So when you define paths, can you define multiple paths out of the same location?
Out of the same location, yeah. So we have done this in, I think, the inverting amplifier, right? So there's one path out of the amp minus node, and there's another path out of the amp minus node.
So why is one here like overlapping and make up the set?
Yeah, no. So when they start at one position, it means their starting point is at that point. So it's only that point that overlaps. Wait, are you asking about like if two paths happen to like overlay with each other?
Yeah, like if you go back to like the band aspect, where you have like one that's going
Here?
like one that's oh shoot, no, sorry, I meant like you have one that's going like all the way to the left, and then you have one that's like sort of curving downwards. So
Oh, like this place?
or from the positive terminal.
From the first positive terminal. Oh, I see what you mean. Yeah. Okay. So yeah, should be okay. So the way this works, so let's also look at this section. So okay, so the reason why this works is for the first one, they're building a short wire going 1 unit left, right? So there's this one path with the resistor being drawn. The other path here, however, is a position plus another node. And the plus here just means they're adding the coordinates together. So this is a more complicated syntax. That is like an application of relative.
Okay, so if you want to start a path from like a position relative to another point, can you just use the relative thing there?
Yeah. Yeah, so that's what the circuit does. So that's what the syntax does. All right, other questions? The overview.
Yeah.
Oh, okay, here. Wait. Dot straight slash. It's the, do you remember like the structure for that? Oh, okay. So this one? Is it the oh wait, I think I know which one you're talking about. You're talking about this one, right? Okay, so this means we're going to the horizontal vertical corner. So we go horizontal first and a vertical later. That's what the symbol originally says. And having this just means we're going horizontal from top left and then going vertical to arrive at M out. So then this position by itself stands for the corner at which we turn at. Yeah. Yeah. So we can, I don't know if this makes sense to LaTeX, but alternatively, we can also think of it in the brain like this. So I go vertically from MPout and then I go horizontally towards top left, right? So now this is the vertical horizontal corner, which should be the same thing. Let's see if LaTeX thinks the same way. But this is how you can also translate it in the brain. So yeah, LaTeX thinks of this in the same way. Okay. Yeah.
One other thing I was wondering is like, if you have these like components defining other files,
Hmm.
and let's say you want to use it on like a really big circuit. So when you define it here, you define it with respect to down. But then let's say you want this entire like sort of subcomponent to be like offset like some like diagonal now.
Oh.
How do you do that?
So like reference the circuit from another one, from another file.
Yeah, like let's say like you have like you want to use this in like a bigger circuit, except you want it to be like centered around like 10, 10.
So to do that, the fundamental LaTeX mechanism is, well, actually, I'll preface the answer. Well, I'll first preface my following solution with I don't really know yet, but here's how I guess Stack Overflow might talk about this. So in LaTeX, you can label figures, right? So in this case, I'm guessing Circuitikz might have another way of letting you label one circuit. And if you want to use this circuit and another different circuit diagram by like directly inserting it in, then what you want to do then is reference this circuit by its figure name, which Circuitikz probably has a way of handling. If it doesn't, then you'll have to copy paste the entire thing.
Is there like a way to set the origin location to be like some variable, and then like pass that variable in as like when you actually file?
It is possible, but I don't really know how global variables in LaTeX work yet. But another thing is, well, let's say that you have another circuit here that is like the big circuit. And you want this circuit to, what am I saying English sentence in 3 times in repetition? But if you want this circuit to start at 10 comma, if you want this big circuit here, and you want this other circuit to start at 10 comma 0, then you can first paste the big circuit here. And if you use it within the same Circuitikz environment, then the coordinates will all become served. So once upon copy paste, you can then use 10 comma 0 here, and that will change where the circuit starts. So that's one other way. You can also define a variable in LaTeX, but that will take a little more time. But if it's working, then it is a good solution. Other things we should talk about? Okay. Last minute clarifications? Okay. We'll see you at meeting then. Oh wait, someone asked on Zoom. Okay, so actually, are people still here? Oh yeah, people are still here. Okay. If you want to draw a current on the arrow, you can. I'll send the slides later, and everyone can reference it later. But if you want to draw arrows on a wire, the correct choice of argument for that is. Let me try to hide this. The correct choice of that is using F equals or I equals, as shown here. Okay. I don't really like how Zoom meeting works. Okay. Any other questions on Zoom? If not, I'm going to close the meeting and I'm going to go host the next review section. Okay, yeah. All right, see you all at meeting then.